In this session, we talk about some basic characteristic of the second order plus time delay model response. Before going into the second order model, we summarize the response for the first order plus time delay model. Now, the first order model equation is represented by this in the differential equation form. Here there are the parameters tau and k. Tau is the time constant and k is the gain. So in the Laplace domain, this is expressed as the transfer function is expressed as k over tau is plus 1. And for an input signal that changes as a step manner, where m is the size of the step and delta naught is the Dirac delta function or the unit step function, we get the solution, this equation yt km times 1 minus exponential negative t over tau. Now we looked at the responses for different values of k and tau. Now let's compare three responses here. One, what we call this base model, k over tau is plus 1, and we took two other models where for one case, for the second case, k1 is greater than k and the tau1 is equal to tau, and for the third case, tau1 greater than tau, the k2 equals k. Now if we look at these three responses, this yt, this is our base response, and for model 1 we see that because the k1 is higher than k, the response goes far away. For model 2, we see that the k2 equals k. So for this case, what we have, the both responses go to the same final value. However, for model 2, the response is slower compared to the base model. So these are the effect of these two parameters. So gain dictates how far the response will go. The time constant will dictate how fast the response will go to the final value. Now let's look at the effect of time delay. So for the base model, we didn't consider any time delay term, or it's equivalent to saying that time delay equals 0. Now if we have a time delay of theta, value theta, then we see this is the base model where the step response start right at when the input is changed, but for the model with delay, we have the response starts after a time theta. So that's the effect of the time delay. So if we have this k, tau and theta, you can get the response for different values and see the effect of these parameters on the response. So that's about first order model and first order plus time delay model. For the second order model, we will not consider the time delay term explicitly. However, the time delay can be considered in the same way as we have considered the time delay term for the first order model. Now for the second order model, the ordinary differential equation can be expressed in a general form, having this order 2, and the transfer function again, the denominator having an order 2. So this is the general form of second order ODE model and the second order transfer function model. Now we have more parameters compared to first order. We have the k, we have this tau, we have this, what they call this xi or zeta, these three parameters, and if we add this time delay, there will be the fourth parameter. So for simplicity, we will keep the time delay term out and we will consider the effect of these three parameters. Now k again, it's called the gain, and it's the change in output per unit change in the input at the final steady state value. And tau determines the speed of the response, and this xi or zeta, whatever symbol you use, this is called this damping coefficient, and this determines the degree of damping. Now let's look at the solution of this equation for a step change in the output. So if us is equal to m over s, we'll have this ys equals km over s times tau squared s squared plus twice zeta tau s plus 1. Now if you plot this function, the shape of the function will depend on the value of this xi or zeta, the value of the damping coefficient. We see if the damping coefficient is greater than 1, we'll have response like a first order response. For this damping coefficient equal 1, also will have response like a first order response. The difference will be for first order response, initially the change will be sharp. For second order, it's initially the response a little bit sluggish. However, if this damping coefficient's value is between 0 and 1, we'll have something like a oscillatory response. So that damping coefficient determines what will be the shape of the response curve. Now, depending on this, we'll have the solution of the equation will have also different form. So if this damping coefficient greater than 1, we'll have the yt expressed as this. So you see that we have only exponential component in the equation. Okay. Now if we have this damping coefficient equals 1, this case what is called this critically damped, and we'll have the solution to be in this form, where again we'll have an exponential term. We see that the first order solution had also exponential term, and we have the second order equation also having the exponential terms. Now the third case, where this damping coefficient between 0 and 1, we see that we have a solution, although it's a little bit involved. We see there is an exponential term, the cosine term, and the sinusoidal term. Okay, so this is what is called underdamped. And we know that if we have an exponential component and a sinusoidal component, these two together will denote an exponentially decaying sinusoidal function. Okay. Now, depending on this value of this damping coefficient, three types of responses are defined. When the damping coefficient greater than 1, we call it overdamped. When the damping coefficient equals 1, we call critically damped. And the damping coefficient between 0 and 1 is called this underdamped, okay, meaning an oscillatory response. Now, one thing to note that both overdamped and critically damped process will model as first order plus time delay. However, for this underdamped process, it cannot be modeled at first order, so it must be modeled as second order process. Now let's look at the effect of these parameters on the response. So all these are second order response for different values of this damping coefficient. Now for this one, really that's damping coefficient equals 0. And you see that this is the sinusoid is continue and there is no decaying function, meaning for this case really this is not underdamped, this is also called what is called this undamped. Okay, so we said that the value of this damping coefficient less than 1, however greater than 0, that determines the underdamped. When it is 0, it's not within the category of underdamped, rather it is called this undamped response. Okay, now if we look at the effect of this tau, then what is the effect of the parameter tau on the response? We see here that for different values of tau, when tau is increasing, the value that it goes, the maximum value that is got, it does not change on tau. These three are for the same value of this damping coefficient. So the maximum value that it reaches does not depend on tau. However, you see like the period of this oscillation depends on tau, and also so the other parameters also depend on tau. Now let's look at what are the different characteristics of a second order underdamped response. This is very important to note that these parameters are used universally, so you need to know the terminology. Here the first term has to call this rise time. This rise time is nothing but the first time, so the step response started here, it oscillated and finally became steady at some value here. Okay, so although it becomes steady at that value, it reaches that particular value several times here, here, and becomes steady at that particular value. Now the first time it reaches that value, that's what is called this rise time, or known as this TR. Okay, then what is the time to first peak? Okay, it's understandable that the term itself means what is that particular parameter. So the time to first peak is nothing but the first time it reaches the peak, meaning that if this is the first peak, how long does it take to reach that particular peak is called this TP, or this time to reach first peak. Okay, now there are two other important parameters. One is overshoot and decay ratio. Now this term, you see the response goes beyond this final steady value by some value A. So this is A, and if this is the final steady value is B, then A over B, that's what is called this overshoot. Okay, and it reaches this first peak and then again goes to a lower peak and comes back to the peak again. So if this is the magnitude of this peak is C, this is A, the decay ratio is called this C over A. So what is simply saying that the overshoot tells how far it goes beyond the final steady state value. The decay says how this oscillation is decaying. Okay. Finally, there is another term what is called this period of oscillation. So if this is an oscillating factor, the period of this oscillation is called this the period of oscillation for this particular second order response. Now all these parameters, they depend on the model parameters. So if you look at what are the relations between these terms and the model parameters, and without going into details, just simply present here this relation. So this TP depends on both this tau and this damping coefficient. And we already showed that the value of this overshoot, that does not depend on the tau value. So there is no tau in this expression here, but there is an exponential relation between this and this overshoot. And to have this decay ratio also, it depends on this damping coefficient and not on the tau value. The period of oscillation, that depends both on tau and this damping coefficient.